we're finishing up our notes for 57, which is interpretations and applications of the derivative and the definite integral. We have two more word problems and lots of questions that go along with them, starting with a pan of biscuits being removed from an oven. When the pan of biscuits is removed from the oven, the time is 0 minutes. So that's like when the timer starts. And then we look at the temperature of the biscuits. As soon as you take the biscuits out of the oven at time t equals 0, the temperature of the biscuits is 100 degrees Celsius. The rate at which the temperature of the biscuits is changing is modeled by this function b prime of t. It's a function with e to an exponent, which has a variable in it. We will plug that into our calculator as x's, of course. So I went ahead and plugged this in as y1, so go to y equals and type all of this in. Okay, number 1, find the value of b prime of 3. So you are plugging in 3 for t here. Let's use the calculator. That's going to help us do this very quickly. So I've got this plugged in, and I'm going to go to table and see that at 3 we get negative 8.236. Quick enough. Okay, so what does that mean? The 3 means time is 3 because 3 replaced a t. So t equals 3 minutes after the biscuits are removed from the oven. Okay. B prime of t was the rate at which the temperature of the biscuits is changing. Okay, so in our sentence, we're going to say the temperature of the biscuits and generally after we talk about whatever the object is or the item that is changing, we say like is increasing or decreasing. Because b prime was a negative number, we're going to say is decreasing at a rate of, and since we said decreasing, we no longer need to put the negative. In fact, we are not allowed to put the negative anymore, 8.236. We need a label. Anytime we are asked to explain meanings, we 100% need a label on this. B is the temperature. B prime is how fast the temperature is changing with respect to time. So this is like b of t with a d dt in front of it, db dt kind of a deal. So this would be degrees Celsius, and then time is measured in minutes. Cool. Next one, sketch the graph of b prime of t on the axes below. So thinking about it to start with, this is e to an exponent. Normally, e to the x looks like this. That's normal. Y equals e to the x. We have some issues though. Let's kind of zoom in on here. We have a negative number in front of e. That flips your graph upside down. Like this. So this would be y equals negative e to the x. But then we have e is to a negative number instead of to a positive number. Okay, so that graph is going to look even different. This would be y equals like 1 over e to the x. And negative, of course. Negative 1 over e to the x would be something like this. If you think back to earlier classes that you took, if there was a negative exponent up here, what that meant is that you would have decay instead of growth. So the decay means that you're getting closer and closer to the x-axis, and then because this is negative, it's flipped upside down. Okay, you are allowed to use a calculator on this problem, so you can also just kind of like graph it out. I'm going to change the window so that we can see it kind of down below. We don't really care about the x's, but we care about the y's. Let's make that negative 100 for y and see what happens there. Woo. Fantastic. We can see the exponential decay because we are getting from really, really big numbers to really, really small numbers close to 0. Cool. moving right along. This graph looks something like this. Probably show you. There we go. That is just kind of copied from what we had before. I'm going to go back to my table and I'm going to figure out where this should actually hit. Okay, if this wants to. There we go. -13. Okay, so I guess it's like way down here. I'm going to make that -13. So just get rid of that scale. Oh, duh. Oh my gosh. If you plug in t equals 0, anything to the 0 power is 1. So -13.84 would be your y-intercept. Mrs. Campbell, come on. Get a hold of yourself. Okay. Explain in the context of the problem why the graph makes sense. So like, why is it down here? So we talked about like mathematically why it's like this, but why does b prime of t look like this? Okay, b prime of t is a negative number. It's always going to be negative because e to any power is always going to be positive, like on this graph, right? This is just e to any power, always positive. So if you multiply it times a negative number, it should always be negative. Okay, what else? The temperature would have been increasing if it was e to the x. Oh, yeah, temperature, oh my goodness. So this graph right here, since b prime is negative, it's all below this axis, that means that your temperature is decreasing. I know the graph looks like it's increasing, but that means that b prime, your rate is increasing. Okay. So where are we over here? B prime of t represents the rate at which the temperature of the biscuits is changing. Boom, that comes straight from this problem. After the biscuits are removed from the oven, the temperature B of t must always decrease, which means that B prime of t must always be negative. Okay, this is shown because the graph is below the x-axis. There we go. Next one, at time t equals 0, what is the temperature of the biscuits? Show your work. So we are looking for B of 10, not B prime of 10, because B is the temperature, B prime is the rate of change of the temperature. So this is a thing we don't know. We know things about B prime of t, which would mean B of t is the integral of B prime. But we always know that if we have one value like B of 10, we need to know another value like given to us in the problem. Like maybe B of 0. They tell us in the problem that at time t equals 0, the temperature of the biscuits is 100 degrees Celsius. So comparing these two guys, B of 10 minus B of 0, if we can find the difference between those two, we can figure out what B of 10 is, which is pretty great. That's going to equal the integral from 0 to 10 of B prime of t, right? Derivative of B is B prime, so the integral of B prime is B. Let's take a little dt right there. Okay. We have the function for B prime of t, and of course we have it plugged in as y1. So let's go to the home screen. I'm going to hit second and then mode for quit. Get to the home screen. Math 9 gets us to an integral. We're going from 0 to 10. And we want y1 to go in there. You can go to vars and get to y1. I recently learned that you can hit alpha and then the trace key to get to F4. And that gets all of your y's as well. Kind of neat, right? See, y vars show up here. There we go, y1 of dx. And we get negative 65.817, 3 decimal places. Negative 65.817 equals B of 10 is the thing we don't know, minus B of 0, which is 100. And then we are solving for B of 10, so we add 100 to both sides. B of 10 equals 34.183. Yay, we should probably take a label for that. B is temperature, so this is going to be degrees Celsius. Awesome. Next page. We have a cylindrical can, which is a normal can. Draw a little can here. The radius of that can is 10 millimeters. I'm going to put 10 here. It is used to measure rainfall in Stormville. Oh my gosh, that's right on the nose, isn't it? Okay, during the first 5 days of a 60-day period, 3 millimeters of rainfall has been collected. So 3 millimeters of rainfall means that from the bottom of the can, if you measure 3 millimeters up, that's how much rain was collected. Okay, it doesn't matter about the volume or anything. We're just looking at the height change. That's how you measure rainfall. The height of water in the can is modeled by the function S, where S of t is measured in millimeters and t is measured in days, and t is between 5 and 60. Okay, so we're told that in the first 5 days, we have 3 millimeters of rainfall. We already know that. So that seems to be that S of 5, because 5 days is how many millimeters of water the height is. S of 5 equals 3. Right? S of t is millimeters. We had 3 millimeters. T is 5. That was our time. Awesome. The rate at which the height of the water is rising is given by the function S prime of t equals that garbage equation with a sign. Okay, I've got that guy plugged in to a calculator as y1. Okay, so I've got that in there already. Make sure that you put the point before the 0 and the 3. That was a common mistake when I did this problem last year. Okay, just make sure you get that decimal in the right spot. Okay, we want to find the value of S prime of t dt from t equals 10 to t equals 15. Using correct units, explain the meaning of this value in the context of this problem. Okay, so the integral of 2 sine of 0.03 t plus 1.5, toss some brackets around that, dt equals what? We can toss that in our calculator. Technically, you should be able to work that integral out by hand. We haven't really done sine and cosine problems yet, though, where there's a number in with t. So we technically do not know how to do this yet. We will learn, just not yet. All right, I'm going to quit out of my y equals and go to math 9 to grab an integral from 10 to 15 of y1. To get to y1, you can hit F4, which is alpha trace, and number 1. And then dx, we get 11.159. Okay. What this represents, remember how integrals work? This is going to be S of 15 minus S of 10, right? That's what that means. If S prime is inside the integral, you subtract the normal function, 15 first, 10 second. So the difference between the height of the water in that can is 11.159. So this integral represents the change or the difference in height of the rainwater in the can, or the amount of water, probably amount of water in the can from t equals 10 to t equals 15 days. Of course, we always have to put our t equals things in there so that you actually know what's going on in the problem. Cool. At the end of the 60-day period, what is the volume of water that had accumulated in the can? Okay, so we start with 3 already, right? We start with 3, and then we want to know how much total water has accumulated after 60 days. So it seems like if we can figure out from 0 to 60, that integral of s prime of t dt, that will be how much water we have. Cool. We don't know, though, s of 0, right? This is going to be like s of 60 minus s of 0. We have to know one of these guys. This is the one we're looking for, so we have to know what s of 0 is, and we don't. What we do know is s of 5. So I'm going to exchange the 0 for a 5. S of 60 is still how much water is in the can after 60 days. It's okay that this number is not 0. Okay, let's figure this out. We are going from 5 to 60, so we're going to use that same integral. Let's use copying this integral and then just change the limits of integration. The limits are the b and the a bits. Okay, so we're going from 5 to 60, and we get 163.565. 163.565 equals s of 60 minus s of 5. So the height at time 60 minus the height at time 5, which is 3. Okay, so this represents the change in the height of the water between these two times, well, those two times. So there's also 3 millimeters of water that were already in there, so let's add 3 to both sides. And we get 166.565 equals s of 60. Yay! Volume of water. So this is going to be millimeters as the height. It's the height of the water after 60 days. This does not ask you for the height, it asks you for the volume. Interesting. So how do you find volume of a cylinder with a height of 166.565? Now, the can itself probably isn't this tall. It is probably taller than that to accumulate more water. But the water, as it fills up the can, is going to fill up in a cylinder shape. So this is going to be the water that is inside the can. Has a height of 166.565, and then the radius equals 10 millimeters from our original problem. Volume of a cylinder is pi r squared, which is the area of the circle, pi r squared, times the height of the cylinder, h. So V equals pi times 10 squared times 166.565, which is totally could have done that without a calculator. 56.5 pi, right? That's just 100, so I moved the decimal over twice. And then if you want to multiply it by pi times pi, there we go. Volume equals 52327.938. This is 3 dimensions, millimeters cubed. So either one of those guys would be okay. Next, the rate at which people enter an auditorium for a concert is modeled by the function r. That's that function. Okay, and you know what? That's just a polynomial. That's not bad at all. We could totally do that by hand for an integral or a derivative. R of t is measured in people per hour, and the time is only between 0 and 2 hours. VIP tickets were sold to 100 people who are already in the auditorium when the doors open at t equals 0. Okay. The doors close and the concert begins at t equals 2. If all of the VIP ticket holders stayed for the start of the concert, how many people are in the auditorium when the concert begins? Yeah, you're not going to buy a VIP ticket and then leave before the show starts, right? That would be silly. All right. Okay, so this is going to be the sum of something, dt, equals something minus something. This is absolutely going to be one of those fundamental theorem of calculus problems. It looks like our two different t values are going to be 2 and 0, right? We're trying to accumulate how many people are actually in this concert. The rate at which people enter the auditorium, that's going to be our r of t. Okay, there's already 100 people. That's going to be this number. And we don't really have a label for these. We can't use r again because this is r. How about p? Which would mean that p prime of t would be the same as r of t. Okay, the rate at which people enter the concert is like p prime. Cool. So we can do this one by hand. 0 to 2 of 1380 t squared minus 675 t cubed dt equals p of 2, like how many people are in the concert at the end of the 2 hours, minus p of 0. There were already 100 VIP people in there. Okay. Over here, we're going to take that integral. So that's going to be t cubed, and then what is 1380 divided by 3? That is 460. Minus, that's going to be a t to the 4th power. Ew, that's going to be a decimal. 675 divided by 4 is 168.75. And we're going to evaluate this from t equals 0 to 2. Now, if you think about it, if you plug in 0 to both of those spots, you're going to get 0. So really all you have to do is plug in the 2, but you have to show that you're subtracting a 0. Okay, so the reader knows that you know that the fundamental theorem of calculus means that it's going to be like bracket minus bracket. Okay, so this is 460 times 8. I'm just going to go ahead and do this math. 460 times 8, which is our 2 cubed, is 3680 minus the 168.75 times 2 to the 4th, which is 16. That is 2700 minus 0 minus 0. That's all 0. So 3680 minus 2700 is 980, which is p of 2 minus 100, p of 2 minus 100, which is p of 2 minus 100. Okay, then to get p of 2 by itself, we're going to add 100 to both sides, and we get 1,080 people is the number of people in the auditorium at the end of 2 hours. Yay, people total. The 980 is how many people showed up in between those 2 times. 100 is the people who were already there. Yay.